Okay, let's analyze another example. So here we have a relationship model. And in this model, Romeo is negatively affected by his positive feelings. So if he feels good about Juliet, it causes a reduction. If he feels bad, it causes an improvement. And then he's positively affected by Juliet's feelings. Here, Juliet is negatively affected by her feelings, and her feelings don't even depend on whether or not Romeo likes her. Really a bunch of dysfunctional people here. So it's we're going to transform this into a matrix equation. So the coefficients go here. And to solve this system, we need to know stuff about this matrix. So we need to know its eigenvalues. And, as I do this, go ahead and pause. Find the eigenvalues. Find them for me. See if you're on track. So it's going to be the determinant of -4 minus lambda, 3, 0, -1 minus lambda. I'm going to set that determinant equal to 0. I'm going to find the lambdas to force this condition. So the determinant then will be -4 minus lambda, -1 minus lambda, plus 0 equals 0. I can pull these minuses out to make this a little easier. Equals 0, and these are a plus. So this was easy this time. So we have eigenvalues, that's not it, -4 and -1. So we can already tell that in our solution we're going to have decay. Our solution is going to look like this. It's going to be a constant. It's going to be e to an eigenvalue, here's one of them, t, times the eigenvector or an eigenvector associated with that eigenvalue, plus another constant, e to the minus t, plus the eigenvector associated with that eigenvalue. So let's go ahead and find the eigenvectors. Again, try to do this yourself first. Okay, let's go through it. I go back to the eigenvalue equation. The matrix acting on a vector is a multiple of the vector. This is fundamental. So I'd have -4, 3, 0, -1, acting on some unknown vector and returning -4 times that. So this gives me an equation, -4r plus 3j equals -4r. So look, if I add 4r to both sides, I'll get j equals 0. So there's no condition on r. R can be anything, but j has to be 0. So eigenvectors that look like this. 1, 0 would work, or any multiple of that. I'll use 1, 0 up here. Now the other eigenvector, again, still using the eigenvalue equation. This is fundamental equation. So set this up. This time we're looking for an eigenvector that has an eigenvalue of -1. So we'll do this out. We'll get an equation, a condition. What do we have here? If I add 4r to both sides, I'll get 3j equals 3r. So j and r just have to be the same. So whatever they are, 1, 1, 2, 2, doesn't matter. So now I have my eigenvalues and my eigenvectors. Now we're going to sketch some solutions. All we've found so far is an infinite number of solutions. I'd like to narrow that down a bit. Oops. So let's make a graph. These graphs, there's a lot of important thinking that goes on when you're doing them. So they're really quite worth the trouble. They're time-consuming, so in that sense, you can't do a lot of them very quickly. But you don't have to do a lot of them. You just have to do a couple of them really well. And if you get stuck in the reasoning, then it generates a question that you can ask me. All right, so let's see, 1, 1. So this is one of the eigendirections. Right? This corresponds to the lambda equals -1 direction. And then we have a 0, 1. I'm going to need a thicker marker for that. And that's I hat, essentially. So right, this corresponds to lambda is -4. So these are our two our directions. And let's start by analyzing them. So by that, what would happen if we had an initial condition on this line? What would happen if you started here? Well, that would mean that the A2 is 0. Well, if you start on this line, then it's just exponential k into the center, right? It doesn't matter which side you start on. So we can put some arrows here. If you start on this line, you stay on this line. And you go into the center. What happens if you start on this line? If you're starting there, that's the same as A1 being 0. So if you start on this line, it's exponential decay, so you also go into the center. Right? Okay. So then this does become a stable equilibrium. Right? It will anyway. Now let's think of some other points here. What about, say, this one? Right, so there's a pencil. This is R equals 2, J equals 1. What happens here? Now, these eigenvectors aren't orthogonal anymore. That's okay. You can still decompose them, parallelogram style. So you still have an amount of, let's call this second vector V2, and this first one V1. So you have some amount of V1, you have some amount of V2. All right. Now what happens from here? Well, both of them decay, but V1 decays faster. All right. Let's put some numbers to this so we can get our heads around it. You know, you take e to the -4 compared to e to the -1. So after 1 unit of time, e to the -4 are at 1 or 2% of what we used to be. And here we're at like 37%. So about 100th or 200ths versus a third. Right? So here we're essentially all the way over. But here only about a third or 2/3 of the way down. So we're going to go from here, and we're going to do something just like that. Now why like that? Because I'm decaying almost all the way. I don't want to draw on the line there. So we're going to end up, say, right about here. So there's a couple of ways we could have gotten there, right? We could have gotten there, say, something like this. If we were decaying faster parallel with this direction and slower with the other one. But we're not. Right? We're decaying faster in this direction. There's e to the -4t in this direction, e to the -1t in this direction. So this is what's going to happen. And it'll get to the origin in infinite time. Right? So this path has finite length, but it takes forever to get there. What about a point way up here? What would happen? Same thing. We're going to experience a lot of decay very quickly in this direction, and slower decay in this direction. So you're going to see something very quickly. You kind of pulled right in there, right? And then, of course, stuff right here, it's going to get closer and closer and closer because there is decay. So you're going to see, it's like, what would happen here? Quick little bit. So he's going to dovetail these things. So you're going to have things kind of being sucked in here. And then anything along this being pulled in. Now take one of these, for example. What do we have here? Well, the decay is now very quick in this direction and a little slower in this direction. All right? So we're going to see this kind of behavior. All right? And what if it was way over here? We're going to see a lot of this motion for a little bit of this motion. And a lot of this motion for a little bit of this motion. And a lot of this motion for a little bit of this motion. And a lot of this motion. So we're going to have this curve that just gets pulled right in. Right? So things are being sucked into the origin there. Right? And, what about something like, you might think halfway out it goes down, but it doesn't, right? Because again, it's more this way than this way. So it's being pulled towards these axes because the other axis is decaying so quickly. Right? So, we're at 12 minutes already. Let's do one more. What did I do? I don't know, choose something. Or maybe on the axis, like what happens right here? Well, again, at this point, what do we have? We've got decay in this direction, or we're moving in this direction. Decay in this direction, or we're moving in this direction. And of course, we're not going to cross this line because these exponential terms, they're never zero, right? They never eliminate the amount of vector in the other direction. They just get arbitrarily small. So they're getting smaller and smaller. So there's less and less of it left. Right? So getting sucked into this origin, getting pulled in. So quite a bit different from before. How about something way out here? What happens to this one? Right? Well, again, a bunch in this direction, a little bit in this direction. That's kind of like what I did over here, right? A bunch in this direction, a little bit in this direction, a bunch in this direction, a little bit in this direction, until it ends up in there, right? So, in fact, there's the potential, if you're way out here, as you're coming in, right, to be decaying so much in this direction that there is almost a boomerang effect. It's not a boomerang effect. It doesn't turn around. Not relative to these axes anyway. But it's decaying quickly in this direction. But at some point, it's small enough that the decay in this direction takes over. So again, you can check your work. You can look at a vector field calculator. Do so. How did you do? How close are you? These are things that you can check. You can build some intuition of.